Hi, today we're going to be looking at higher order derivatives. So what this means is we're not just looking at our first derivative like we've been doing so far. We'll actually be taking our second derivatives, third derivatives, and so on. So I just have some definitions for our derivatives on this page. Our first derivative is what we've been doing so far. So that's our y prime is dy dx. Second derivative we can denote by having our prime symbol twice, or we can do dy prime over dx, or we can have d over dx times dy over dx equals d squared y over dx squared. For a derivative, we can use triple prime. This part we just add a second prime symbol. This part we just change it into squared. And then over here, d cubed y. So these are our general notation for derivatives. Now for our nth derivative, that's yn equals dyn minus 1 over dx equals d dx of dn minus 1y dxn minus 1 equals dny over dxn. So first example we're going to look at is finding the second derivative of y equals 5x squared plus root x. Now, to get our various derivatives, we have to do them in order. So if we're solving for our second derivative, we first have to find our first derivative. So to get our first derivative, we know that's just d dx of 5x squared plus the square root of x. So that would just be d over dx of 5x squared plus d dx of the square root of x. So our first derivative is 10x plus 1 over 2 root of x. Now to take our second derivative, we're just taking the derivative of this again. So that's d dx of 10x plus 1 over 2 root x. So that would be d dx of 10x plus d dx of 1 over 2 root x. So our second derivative is 10 minus 1 over 4 square root of x cubed. Okay, so we'll look at one where we're doing more derivatives. So we're looking for first 5 derivatives of y equals x to the power 4 plus 2x cubed minus 5x squared plus 3x minus 6. So our first derivative, we just take the derivative of everything. So x to the power 4 plus 2x cubed minus 5x squared plus 3x minus 6. So that would be the same as saying d dx of x to the power 4 plus 2 d dx of x cubed minus 5 d dx of x squared plus 3 d dx of x minus d dx of 6. So our first derivative is 4x cubed plus 6x squared minus 10x plus 3, and then this we'll get 0 from. So getting our second derivative, we just take the derivative of this, So we'll break this down. So this is our second derivative is d dx. Actually, sorry, is 4 times d dx of x cubed plus 6 d dx of x squared minus 10 d dx of x plus d dx of 3. So our second derivative is 12x squared plus 12x minus 10. Now our third derivative, we just take the derivative of this whole side again. So d dx of 12x squared plus 12x minus 10. So breaking that up, that's 12 d dx of x squared plus 12 d dx of x minus d dx of 10. So our third derivative would be 24x plus 12. Now to do our fourth derivative, we're doing the same thing again. So d dx of 24x plus 12. So that's 24 d dx of x plus d dx of 12. So our fourth derivative is just going to be 24. Now our fifth derivative is d dx of 24 which is 0. So our fifth derivative of this is 0. Now, these higher order derivatives aren't simply for only for ones where we have explicit equations. We can also do it with composite functions. So for example, if we're given f prime of 3 is equal to -1 and f double prime of 3 equals 2, we're going to find the value of d squared of dx squared of x f of x at an x value of 3. So first thing I'm going to do is say let y equal x f of x, so x times f of x, and we'll find our first derivative, so that would be d dx of x times f of x. So we have to apply the product rule now. So that would be f of x plus x times f prime of x. So this would be our first derivative. Our second derivative would be d dx of f of x plus x times f prime of x. So that is dd of x, f of x, plus d dx of x times f prime of x. So that makes our second derivative f prime of x plus, we have our product rule here, so f prime of x times x times f double prime of x. We'll just reorder some of this in next line. So we've got y double prime, our second derivative, is f prime of x plus x times f prime of x times f double prime of x. Now we'll start filling it out. We want to assess it when x equals 3. So our second derivative when x is equal to 3 would be f prime of 3, so that's -1, plus our x, which is 3, times f prime of 3, which we know is -1, times f double prime of 3, which we know is 2. And just looking at this, I realized I made a slight error when we did our product rule here. So we would have had, or sorry, our product rule up here. So I'll just go back to that step. So we had y double prime equals our derivative of f of x, which is f prime of x, plus our derivative of s. So s would be plus f double prime of x, or sorry, f single prime, because when we take to our product rule, it's derivative of this, which would be 1 times this, so plus f prime of x. And then we have plus x times the derivative of this, which is f double prime of x. Once again, sorry that I was going a bit quick and made that small error. So now that we've got this, we can assess it when y equals 3. So that gives us -1 plus -1 plus our x value of 3 times f double prime of 3, which was 2, and we get a value of 4. Okay, next example. We can also deal with implicit differentiation with this. So we've got if x cubed plus y cubed equals 5, use implicit differentiation to find y double prime, our second derivative of y. So we'll start by taking the derivative of both sides. So we have d over dx of x cubed plus y cubed equals d over dx of 5. So this is the same as d over dx of x cubed plus d over dx of y cubed equals d over dx of 5 is just 0. That gives us 3x squared plus 3y squared times y prime, which is our dy dx, equals 0. I'd move the 3x squared to the other side, so we've got 3y squared times y prime equals -3x squared. Divide both sides by 3y squared. So we have y prime is simplifying this -x squared over y squared. Now to find our second derivative of y, that's d over dx of, actually we might as well move the negative in front. That's negative d over dx of x squared over y squared. Now for this, we need to use the quotient rule. So therefore, we have the derivative of this, which is 2x times our quotient, plus this, so x squared, times the derivative of our quotient, so 2y times y prime, over our denominator squared, so over y to the power of 4. So cleaning this up a little bit, that gives us y double prime is equal to negative of 2x y squared plus 2x squared y times y prime over y to the power of 4. At this point, we can substitute in our equation for y prime in for this. So we have y double prime is negative of 2x y squared plus 2x squared y times y prime, which is x squared over y squared. And that's all over y to the power of 4. Now this will partially cancel with this. So that gives us y double prime is equal to negative 2. See, sorry, that negative should be in front of our bracket, our division line. So we've got negative of 2x y squared plus 2x to the power of 4 over y. And that's over y to the power of 4. Now what I would do at this point is multiply the numerator and denominator by y over y. That way we can get rid of this extra fraction. So that's going to give us y double prime is equal to negative of 2xy cubed plus 2x to the 4 over y to the power of 5. Now, something I notice is I can factor 2x out of both these terms, so that gives me y double prime is equal to negative of 2x bracket y cubed plus x cubed over y to the power of 5. Now, if this part looks familiar, y cubed plus x cubed, if we go back to the beginning, is equal to 5. So we can replace this with 5. So that gives us y double prime is equal to negative 2x times 5 over y to the power of 5. So y double prime is equal to negative 10x over y to the power of 5.